I am Professor Anish Vora and I welcome you all in this video lecture. Currently, as you know that we are running a series of video lecture on design of synchronous machine. In this video lecture, we will study design of field winding. In previous lecture, we have studied dimension of pole in case of salient pole and the dimension of the field winding that we have already studied. In today's video lecture, let us start with we have dimension of the pole. Pole dimensions are now known. So this is the pole, and as per the depth of the winding, a field winding is wound across the pole. So if we see from the top view, then we can see this type of dimensions. So the active length, because of eccentricity, active length, that is Lm, and Lm, that is 0.9 times L, and this is our length of the pole, L. We have width of the pole. We have taken a rectangular pole for a design purpose. So this is a width of the pole, BP, and we left 5 millimeter space between pole and field winding. So now we start our design. So first we start with length of the mean turn. We need length of the mean turn in number of calculations. So we start with the length of the mean turn. Depth of the field winding, that is dF. Length of the mean turn of field conductor. So as per the dimension we have seen, just we can derive one equation, that is L and MTF, that is mean turn, suffix MTF, that is mean turn, and F is for the field. So that is equal to 2 times Lm. Lm is active length, Lm, plus pi into bracket BP, that is a width, plus 0.01. As I said that 5 millimeter plus 5 millimeter space we leave on both the sides, so it is 0.01, and plus dF is depth of the winding. So this way we can have, from this empirical formula, we can have a length of the mean turn. Now voltage across each field coil. We normally start designing our field winding with the non-exciter voltage. Exciter voltage must be known from the consumer end. Normally it varies between 50 volt to 400 volt, but normally it is around 125 volt exciter voltage. So if exciter voltage VE is known and number of poles are known, then we can derive one equation for the voltage across each coil. Now 10 to 15% voltage or 15 to 20% voltage will be consumed by the field rheostat or field regulator, and only 80 to 85% voltage will be consumed by the field winding. So accordingly, the voltage across each coil, we have number of poles, and if we divide the total voltage, exciter voltage, by number of poles, then we will get actual voltage across each coil. So voltage across each coil, that is EF, that is 0.8 to 0.85 times VE. VE is exciter voltage, and either it is 0.8 or 0.85. So it is 80 to 85% of the exciter voltage will ultimately reach to the field winding, and divided by number of pole P. P is number of pole. So from this equation, it is very easy to calculate actual voltage across each field coil. Also, we have another equation to derive voltage across each field coil, and it is very simple. Our normal equation, that is current passing through the field winding and the resistance of the field coil. So IF multiplied by RF, that equation also gives the value of voltage across each field coil. So EF, that is a product of IF multiplied by RF. But at this stage, field current is still not known, and RF, that is resistance of the field coil, that is also not known. So both the quantities are unknown, but the equation for the resistance of the field winding we can substitute. So if we substitute equation for resistance of the field winding, we have equation like IF multiplied by TF multiplied by rho. Rho is the resistivity of the copper. LMTF, that is the length of the mean turn. TF, that is number of turns of the field coil, and divided by AF, that is area of the cross section area of the field conductor. So this way we can have another equation for voltage across each coil. Now in this equation we can see that some of the quantities are known. For example, voltage across each field coil, EF, that is known, rho, that is known, LMTF, length of the mean turn, we have calculated at the very first stage. So now let us derive area of the cross section of the field conductor from this equation. So this equation is very important, and from this equation we are supposed to design or supposed to calculate area of the field conductor. So TF, that is number of turns in each field coil. Now field MMF per pole at full load. In previous lecture we have seen that how field MMF at no load can be calculated, and from that value, from the phasor diagram, with the help of phasor diagram, we are able to calculate the field MMF per pole for full load. So that value is known, and that is ATFL. So ampere turns for the full load, FL, that is for the field full load. That is the product of IF multiplied by TF. This is normal equation for ampere turns, current passing through and number of turns. So IF TF, that is our equation for field MMF per pole at full load. Now for the product IF TF, if we substitute value at TFL, then our equation of voltage across each field coil will change like this. So voltage across each field coil, now it has changed, is equal to ATFL multiplied by rho multiplied by LMTF, that is the length of the mean turn, and divided by cross section area of the field conductor. Now from this equation again we can see that now most of the quantities are known. Voltage across each coil, that is EF, we have calculated ATFL, that is a field MMF per pole at full load, it is known, rho, it is known, LMTF, length of the mean turn, we have calculated. So only unknown quantity is the area of the field conductor, that is AF. So from this equation we can easily able to calculate area of the field conductor, and AF, that is ATFL multiplied by rho multiplied by LMTF and divided by EF. So EF is the voltage across each coil. So ultimately from this equation very easily we can able to calculate area of the field conductor. Now if area of the field conductor is known, by assuming appropriate value of the current density, we can very easily calculate field current. So field current, that is current density multiplied by area of the field conductor. Now area of the field conductor we have calculated in previous equation. So if we assume suitable current density, then field current, that is IF, can be calculated, and that is delta F multiplied by AF. Well, delta F, that is field current density, and normally we assume around 3 to 4 ampere per millimeter square. So from this equation we can easily able to calculate our field current. Once we have field current is available, then we can calculate number of field turns. So to calculate number of field turns, that is TF, we know the equation that ampere turns for the full load, that is a product of IF and TF. So from this equation we can easily able to calculate number of field turns. Now resistance of the field winding. Now most of the quantities, most of the parameters we have calculated. So ultimately at the last we can calculate the resistance of the field winding also. So resistance of the field winding, RF, that is equation. Now we know that rho LMTF multiplied by TF, number of turns, and divided by area of the cross section area of the field winding. Now we can see that in this equation all parameters are known, and we can easily able to calculate the resistance of the field winding. So now let us see how we can accommodate our field winding. So height of the field winding, again we see one elevation view of the cut section view of the field winding. So we have considered one salient pole, and let us see how field winding is accommodated, and height of the field winding is important. So this is our field winding, copper field winding, field copper winding, and height of the field winding. See, now at this stage we now have calculated number of turns. So space available, it is known. So if as per the number of turns, if space available is more, then we have to decrease the depth of the winding, and if available space for the required number of turns, if space is less, then we have to increase the depth of the winding. So in both the condition we have to adjust, we have to accommodate our field winding, because height of the field winding is fixed, we cannot change height of the field winding. So we have to adjust the depth of the field winding to accommodate our number of turns now we have calculated. So this is a saliency. We leave certain space, that is for the insulation and for the fixtures like flange. Then we have height of the pole body, that is HP. HP from the design we can see that HF plus allowed space, that is height of the pole body, and then we have at the center of the pole we have height of the pole shoe, that is HL, and HP plus HL, that is the overall height or radial length of the salient pole. So this should be very much clear, and then from this we can have a height of the field coil. So height of the field coil, that is HF, and that is equal to HPL, HL minus space for the flanges, where HPL, that is the height of the pole overall height, and HL, that is the height of the pole shoes. So height of the field winding now it is available, and as I said earlier that the depth of the field coil or field winding we have to adjust. So if we go by a step-by-step design, then it is very simple to design a field winding. Let us revise all the steps in a very quick way. We have in starting we have first we have calculated the length of the mean turn. Then based on the available or non-excited voltage, we have calculated the voltage across each field coil as per the number of poles. From the available data of voltage across each coil, from the equation we have calculated area of the filled conductor. Once area of the filled conductor is available, then assuming a suitable value of current density, we have calculated field current. Once field current is available, then as per the non-full load field magnetomotive force, that is ampere turn available, we have calculated number of turns of the field winding. If number of turns are known, then resistance of the field winding can be easily calculated. So this way, if we go a step by step design, then it is very easy to design or to calculate all the parameters, required parameters of the field winding. So ultimately at the last, we have calculated height of the field coil. We do not have very much provision to adjust the height of the field coil, but depth of the field coil, in previous lecture that we have seen that depth of the field coil depends on the pole pitch. So we have assumed, or we have taken suitable value of the depth of the field winding, but to adjust the calculated number of turns in available space, we have to adjust our depth of the field winding. So now let us proceed further. Design part is over. So now we have to calculate our copper losses. So full load copper losses, if we calculate, then copper losses in each field coil, it is capital QF. F is for the field, and we know that it is I square R type of loss. So IF is field current, IF square multiplied by RF. RF, that is resistance of the field winding. So this way we can able to calculate copper loss in the field coil. RF we have already calculated, else we can put equation for the RF also, and that is IF square TF multiplied by rho multiplied by LMTF and multiplied by divided by area of the cross section. So if we have not calculated RF, then as per this equation again we can able to calculate total copper loss in the each field coil. So at last we have to check for temperature rise. If the temperature rise is within a permissible limit, then our design is perfect. Else we have to change some of the parameters. So for the temperature rise, we know that theta is a temperature rise in degree centigrade. So a temperature rise, that is equation is QF, that is a total copper loss, multiplied by CF. CF is a cooling coefficient and divided by heat dissipating surface. So if temperature rise is within a limit, then as I said earlier that then our design is perfect and we do not need to do any modification. But if temperature rise is more beyond permissible value, then what we need to do is we need to change our depth of the field winding. We need to increase the depth of the field winding. I repeat, when temperature rise is beyond a permissible limit, then the parameter we need to adjust, that is depth of the field winding, we have to increase the depth of the field winding. Now it will help in two ways. First, by increasing the depth of the field winding, current density will reduce, and if current density reduces, then it will directly affect the copper losses. The copper losses will also decrease. Second, if we increase the depth of the field winding, then heat dissipating surface will also increase, and if heat dissipating surface increases, the temperature rise will be less. So to adjust the temperature rise or to check the temperature rise, we have to adjust our depth of the field winding. Now theta, that is temperature rise, and we have seen that equation is QF multiplied by CF and divided by S. where S is a dissipating surface of the coil, and it can be indicated by this equation, that is 2 LMTF and multiplied by HF plus DF. HF is the height of the field winding and DF, that is depth of the field winding. So what I was discussing, that we have to adjust the DF. So by adjusting DF, we can set our surface area, dissipating surface area of the coil. And CF, that is cooling coefficient of the rotating field coil. So in terms of peripheral speed, we can have a cooling coefficient. So it is 0.08 to 0.12 times and divided by 1 plus 0.1 VA, where VA is our peripheral speed. So this way we can check our field winding design. Ultimately, in all the design, at last we have to check for the temperature rise, and we have to see that our design is perfect and temperature rise is within a permissible value of the class of insulation we have used. And the final check, that is a clearance between adjacent field winding. So between adjacent field winding, the permissible minimum clearance should be 15 mm, and that we have to check. So this way we can do a complete design of field winding. I hope it is very useful to you. Thank you for watching my video. Keep watching, and if you like, you can subscribe my channel. Thank you for watching. Again, thank you very much.